Okay, so perhaps we can just start with some background on Solargis, the sort of when, why formed, and any sort of key milestones today. Just give us a bit of background on yourselves, please.
Yeah, Solargy started 15 years ago in 2010, and previously we have been working as researchers in European research, PV research, and that was quite inspiring time. The photovoltaics as industry started to be more stronger, and being researchers, we were quite successful to develop some supporting tools, data for the emerging industry, and it became quite popular. And we saw that this is a good idea, but it cannot stay as a research project. It needs to be converted into industrial solutions. So that was a time also when we decided that we have to probably start a company and develop solution which can support industry in all their needs. So let's not forget that in 2010 roughly, industry was very young. It was just few countries which really supported PV by various incentives. And therefore, also developing and operating photovoltaic power plants was relatively simple. There was not much sophistication around that. But since then, things have changed a lot. So we managed to develop important databases, weather databases, solar radiation and weather databases, because these data are critical for evaluating the energy yield, and understanding what is the energy yield is a first thing you need to have for financial evaluation of the project. So in order to facilitate financing, you really needed a much better meteorological data to calculate the performance and the yield of the project. And therefore, with the industry being more mature and being more supported by investors, it was clear that the data and tools which were supporting such an effort had to be much more sophisticated, more accurate, because with investing tens of millions of euro or dollars or hundreds of millions of euros and dollars, you need to really, you want to be as accurate as possible. So that was the starting of the company. Over time, we developed a global database. We developed web-based channels of distributing data and also software services now. But now the situation is quite different. The industry has grown to be a global, growing industry. Practically, we have customers in more than 100 countries, and this also creates a very different environment. Today, we see the need for much more data, but I will come to this later. Maybe we wanted to just explain the starting of the company.
No, that's fine. And as I understand it, I mean, the technology solutions you offer in the main, or the main one is the focus on long-term data analysis of solar irradiance. Is that right? Yeah.
That's true. That was, yeah, the company started around that. Why? Because the building projects, construction of projects, and financing the project required this type of information. From a long history of data, you learn about what the production is to be expected in future. And if we talk about future, we talk about 25, 30 years. So the longer history of data you have and the more accurate, the better your financial estimate is. And that's where the company started. And this is also one of the important pillars of our commercial operations. So we are supporting photovoltaic power plants in the phase of development. So not only today by data, but also by software, which is more looking into the design, energy yield simulation, analysis, and so on. But we will come to this later. But having already under control the data streams, and now that's important that the technology behind that is based on the global weather observation systems, such as meteorological satellites. We have about 5 principal satellite missions monitoring weather, geostationary satellites, but then there are global meteorological models, forecasting models. So having all this technology under control, receiving global data from the systems, we saw that there is not only value in offering historical data for project development, but also real-time calculated data for project operation. And many people ask, like, okay, if I need a meteorological data for developing a project somewhere, why don't we just use the data from meteorological offices? And the answer is simple. You need a project somewhere in the middle of nowhere, and there is no meteorological station around. The nearest one might be 100 kilometers away. And therefore, the only help here is to rely on models which are calculating all necessary parameters. And today, these models are quite accurate. There was a very strong development effort both in the observation technology. Quality of satellites has been evolved so dramatically. I always like to compare it to mobile phone technology. If we can imagine the mobile phones like 10 or 15 years ago, what kind of services we did have, and now with the recent technology, we can clearly see the difference. And the same applies for meteorological systems, especially satellites. So today, these observation systems, the data from these observation systems can be used in a quite extensive numerical calculations to calculate weather data for any location and with high accuracy. And so today we can calculate not only the history, what has been measured, but also with all the forecasting models, we are able to offer services to forecast solar power production. So this is something so all these technology advancements and also scientific advancements in modeling helped us to extend the services to the entire life cycle of the project, from development up to the operation, monitoring, forecasting, selling data on the electricity market, and so on. And then besides data, we also developed on top of data software services such as energy simulation, forecasting, quality control, analytical tools, and energy design tools, so that you can quickly create electrical design and run some optimization tasks. Okay, so this is all about developing important digital tools which serve the growing needs of industry. And again, this is something where we, over more than 1 decade, okay, maybe 2 decades, if I go really deep into the history, we saw industry emerging so quickly, starting with very rudimental approaches, very supported by some simple Excel sheet exercises and maybe desktop tools, very simple desktop software coming from research lab, by the way. All tools and data which have been used at the beginning at the dawn of the industry were coming from research. And we were part of this research. So that's why we kind of understood where we stand and where we should go. Today, it's majority of solutions offered today are, of course, industrial.
And in terms of one of the sort of fairly significant things you do, I believe you conduct an annual global horizontal irradiation, or GHI, analysis, and that's to help understand, if you like, the impact of higher and lower levels of solar irradiance. So I guess it'd be good to understand if you can share the sort of most recent findings for Europe to tell us what's going on, with these patterns, if you like.
Yeah, maybe let's explain some terms. So solar radiation, that's the energy of sun, sometimes called sunshine, And that's what is actually the energy which powers solar photovoltaic systems, energy of solar radiation. But what is also important are other factors which are affecting the operation of the project, such as temperature, for example. At a very high temperature, the efficiency of the production is lower. Then there are all kinds of other parameters, such as wind speed, pollution, snow, and all these weather data are important to understand how the project operates and what are the possible risks and what kind of demand we will have for the, not only for capex, like to develop good resilient project which can stand all kind of weather extremes, but also how to optimize OPEX, operational expenses, so that we can react to the effects of weather. And now, as we say, it's clear that renewable energy is driven primarily by weather, and solar is driven primarily by solar radiation. When we look back like 15 years ago, there was so little understanding of what is the geographical distribution of solar radiation, where are the more favorable areas, like, and there was almost no information about any kind of variability, like how stable it is and so on. Today, we are in a very different level. We have, for example, for Europe, we have 30 years of high resolution time series data, which allow us to study variability, which is very important today for grid integration. And also we can study trends. And this is what every company, every investor asks us about: how can we rely on historical data to predict the future? As renewable projects are typically designed to operate in the horizon of 20 to 30 or even more years, then there is a clear question, like, how we can be sure that whatever we calculate from the history is valid for future. With climate change, which is happening, we clearly see the temperature, for example. That's a parameter which is very easy to observe, that we have rising temperature in a majority of geographies, in almost all geographies, not everywhere, but almost everywhere. Well, how it is with solar radiation, which is the primary driver of the power production, we see in Europe that there are trends. These trends can be calculated. It could be something like few percent, one to few percent per decade, or and it very depends on the region. So for example, Northwest Europe, we see clearly that the trends are stronger, whereas in Southern Europe or Southeast Europe, it's not the case. So in order not to speculate too much, we just can say that the trend or the variation of weather is normal. That's because weather is depending on a number of cycles of different magnitude. But the trends is something where we see that over like maybe 20, 30 years, we see something happening going one way. And thanks to this technology, high resolution data, long archival data, ability to separate small signals from noise. Let's not forget that we have to combine data coming from different observation technologies. As I said, satellites operating 20 years ago were not as accurate as today, but they still were able to measure physical values. So having all these data under control, being able to spot data irregularities from climate patterns, we are able to calculate those trends and explain investors what they can expect in the location of their interest. So if I build a power plant in southern Spain or northern France, the situation could be different. And that's what is today possible to provide more insights. I would say with climate change, we need to focus on different problems. With solar radiation, there is some cycles variation, which is kind of okay. It could result in some few percent of energy yield going up or down. What is more difficult to predict are the extremes of weather. Whether it is too high temperature, too low temperature, thunderstorms, strong winds. So anything which can dramatically reduce production efficiency of the technical configuration, but the even more serious are those factors which cause damage, physical damage, such as hail, strong wind which has not been recorded before. And therefore, when we talk about energy sector, renewable energy sector, we, besides understanding the long-term trends in solar radiation temperature, we need to also look into data, high-resolution data, which can help us to understand how the wind patterns might affect certain designs. So I will stop here.
No, that's good. I suppose what strikes me is something of an irony that the industry, if you like, came about because of climate change, renewable energy, to address the climate change, which I think, folks understand, has to be addressed. But it seems as if the same climate change is actually impacting the sector. And I mean, I do a lot of work in the water industry, so it's not just climate change, but as I think you've explained there, it's the climate volatility. It's the extreme weather events that are maybe causing the problem, as well as the general direction of travel. Is that right?
Yeah, but Phil, let's understand the renewable energy is in the same situation as any technical assets we have to adapt to changing climate. So, and we are successful in doing that. So we understand much better what are the risks, what are the possible factors to consider in building more resilient designs and better approaches of how to operate power plant. So we have challenges everywhere: water supply, everything like energy, extreme heat in summer, and a lack of rain, and so on, or flash floods like heavy rain coming, well, in one day the rain totaling something which normally comes in 6 months. And this is, of course, affecting everything, including renewable energy assets. What we can do here is to plug in more data, to carefully observe the history, to observe the trends, to develop better tools, to help to optimize designs so that they can withstand the critical events. And what are the critical events? Today, all designs are built to maximize the technical capabilities of the PV modules, inverters, trackers. So that means the structures which are tracking sun. And of course, the design is built to the maximum technological edge, so that there is a maximization of the capital invested, with, of course, keeping operational costs at under control. So when you create challenging designs, like every mistake in calculations or poor data or like data which are not fully representing the local geography might result in mistakes which will in a better situation just cause some disruptions or reduced performance, but some mistakes may result in damage, physical damage. So we cannot control the weather, fortunately, but we can better understand weather. And that's what industry is doing. I think it's not only renewable industry, this is happening everywhere. We simply need to go back and better understand what is happening and to propose solutions which can better adapt to possible risks which we may be facing. We don't know what kind of weather patterns we are going to have in 20 years from now, but with some level of anticipation of certain changes, we can prepare for that. Of course, this is never 100% bulletproof, but it's better than just doing nothing. And in order to protect multi-million-dollar investments, we need to invest into digital technology. And it's we are very comfortable in having a lot of data, high quality data from various systems and computing power, cloud-based systems, modern scientific, new scientific tools which can better react to the challenges.
So, as I understand it, then the solar energy operators are already investing in sort of high resolution satellite solar data, advanced modeling tools. And it'd be good to, I suppose, understand where those are at the moment, you know, how much better they are than, shall we say, the older or traditional tools that they might have used. And the world has gone AI crazy, and I'm assuming that AI has a role to play here, that there'll be, you know, whether it's developing large language models, whatever it is, AI has a significant role to play in further improving the sort of accuracy of the data analysis part of the process. Is that right?
I agree. Definitely. Again, let's put things into perspective. In like 20 years ago, 15 years ago, the solar was very small industry, relying on multiple incentives, fiscal incentives, but also priority to the grid. So developing a project, which was quite expensive actually, was relatively simple, and you didn't have to do much to integrate it into PV, into the grid, and just then there was a simple arrangement with the financial arrangement with the bank and so on. Today, we have tens of gigawatts of assets in every country, which means that we, in summer or in some sunny days, the solar itself can completely cover the energy needs of the entire country, which of course creates a completely new situation. You suddenly have to control everything in a very different way. So the incentive years ago was very different as it is today. That's first thing. Historically, you could just pick up whatever data you found, relatively simple, just maybe sometimes 12 values, long-term average monthly values, and that was it. Even with Excel, you could do a good job of building your financial plan. Now you need sophisticated simulation tools. The data banks are very picky about you choosing the data you want to use in energy simulation. So there are only few suppliers. We are considered as the most bankable, accepted by banks, a supplier globally. And this is because the industry wants to rely on trust that the data is okay, the under control, the software tools are okay, so that because the margins, profit margins are very low, and every mistake can be felt painfully in the financials. Then what is also important that in historically you could deliver electricity to the grid. There was every producer was had priority of access to grid. Today this is not the case. You have to negotiate access to the grid. You have to negotiate prices with the off-taker, with someone who is buying from you, which or you sell on the spot market, which is extremely volatile. To prepare for that, nobody guarantees. Okay, nobody guarantees you that your electricity will be purchased. You need to work on that. That's first thing. Second, you need to sell electricity when needed, when it is when the price is right. So all these tools suddenly require a lot of sophistication. The operational monitoring and forecasting is very important. Without forecasting, you are unable to properly collaborate with the grid operator or with the market. So all these tools are, I mean, digital technology has to support physical assets. It's practically impossible to operate renewable energy assets without proper digital tools and data. What is interesting is not only technically the tools and data, granularity of data are evolving quite dramatically, but also industry and society has to accept that there is a pretty fast change in we are changing the methods how we evaluate projects. We are introducing new KPIs which are to be used for monitoring of the health of the assets. And there is, of course, some latency, some resistance to change. So it's on one hand, you have to deliver technical solution, which is adapting to the requirements of the market. On the other hand, the society and industry has to accept that we need to do things in a different way. And that's, of course, takes some effort. It also creates some challenges on the companies themselves, like you need talent, you need people, skilled people, experts in various areas. For example, in our company, we need we have a multidisciplinary team, which includes geoscientists, IT guys, atmospheric modeling guys, electrical engineering guys. So, and similarly in other companies, the requirement for workforce, skilled, knowledgeable workforce are quite high. And that's also something which is still evolving. But in order for industry to operate properly, the digital tools is one important aspect of success. And it's a story which is going on. It will take some time. You mentioned AI. I can say that while we live in a very physical world, because we deal with physical simulation of systems, with the physical modeling of the atmospheric effects, the solar radiation modeling, there is definitely room in putting on top of physical models some machine learning tools which can help in improving in the boundary between physical world and the stochastic world of weather. The machine learning, for example, can help adding extra value. And this is, of course, something what we are doing. Everybody is doing this. And in general, AI definitely is stepping into various areas of our work. So we need to be sure that we apply physics and physical models where it is more effective. Physics, which simply measures, which takes data from observation systems such as satellites. Satellites are measuring systems which are physically measuring the situation, for example, today, geostationary satellite takes one data set every 5 to 10 minutes with very high resolution, which can go up to like half kilometer. And this is, of course, enormous volume of data, like which cannot be compared to what we had like 10 years ago. And it's on the edge of you have to apply a new processing techniques, of course, cloud-based, parallel computing. You need to start looking into help of other techniques than just physical modeling. So there is definitely room to improve here. And also the problem is that the spectrum of data and is pretty large, and you need to make sure that you are picking those parameters which give you the most important information for your decisions. So in short, yes, it's here. We have to work on with that, with AI and all the other data technologies.
And I guess just to sort of re-emphasize the importance of increasingly granular, accurate data, etc., is right through the process. So it's from maybe choosing the best place to locate a new, plant. It's the operation, optimizing the operation. With AI, potentially you're going to be able to crunch the data and maybe spot patterns and which seen previously and understand what's going on. And as you say, maybe the least easy thing to do is predicting the future, but nevertheless, the data has a sort of crucial role to play sort of throughout this I'll call it supply value chain, whatever you call it, the whole process. Is that right?
I would say you are right. Monitoring the history is to some extent simpler because you are dealing with physical measurements, whether they have been made on ground, like in meteorological stations, automated meteorological stations, or by satellites or by meteorological models. What is important is to predict, to do forecasts, and typically today forecasts, solar power production forecasts, are designed for the future, or which could be in horizon of minutes, hours, up to several days. And this is for operational, for managing the operation of the not only one single power plant, but entire portfolios, which might be connected to the grid. So forecast today, if we say forecast, it means many things because there are various applications of forecast. There are different motivations why we need forecast, whether it is technical to be more supporting grid in managing the variability of weather and variability in demand, electricity demand, but also the forecasting serves for the purpose of trading, for selling electricity on the markets, for stabilizing the grid in the local, regional level by like smoothing the variability patterns and so on. So what is always important is the accuracy. You want to be as accurate as possible, which of course we are much more accurate today than historically, but still, especially for forecasting, we have limits. As even with AI methods, we still deal with stochastic systems, which of course and the granularities and the spatial resolution of data required, which of course is difficult to. We should be very careful about expectations on the accuracy, and we talk about numbers which are related to the single project or multiple projects, where we talk about exactly how much megawatt hours will be produced in our A, B, C. That's different from what we are used to as consumers, like temperature, maybe rain coming, not coming, maybe later in half an hour. For grid, these are important effects. If we are mistaken in forecast by like half an hour because a thunderstorm comes later, or I don't know, this of course creates disruption with the grid operator. They need to prepare for that. They need to have support systems, and we will never be perfectly accurate, but that's fine. We still have other tools to manage those imperfections. So actually, forecasting is dramatically helping renewables to be integrated into grid in a large installed capacities, and to also better understand how to operate grid with having a large volume of installed capacity, whether it is wind, solar. But forecasting also relies on the historical data, so that we should understand what kind of events we can expect, and to see whether we are prepared for them. And a good example is maybe in Texas in 2021, there was a storm in a winter, Uri storm, I guess the name was. And the temperature suddenly became extremely low. The energy systems were not ready for that, and the energy system failed in Texas, ERCOT, and including solar power plants, because they were not able to sustain the low temperature, which was not expected. And why? Because still industry is using traditionally relatively low resolution data, simplified data. We call them typical meteorological year. That's a simple data set kind of representing typical weather with the hourly values, which means 8,760 values. But this data set doesn't tell you anything about possible extremes you may expect. That's why we moved to the use of time series data with higher resolution, 15 minutes up to 1 minute, recorded history, where we can see exactly those extremes which are not seen in the simplified average files. And if you see, and we also demonstrated that if you can work with such high resolution data, you can focus on those extreme events, then you can prepare your design to withstand those extremes. And that's where industry is moving.
Yeah, I mean, to that point, it'd be good to understand how do you think the industry is moving? Is it moving at the right pace towards, these fully using the digital solutions available to them? Is it disappointingly slow? How would you characterize? I know there'll obviously be, companies that are always ahead of the curve and the laggards, but as a general sort of thought, would you say that they're moving at the right rate in the right direction, or are you a little bit disappointed, shall we say, in the speed of progress?
I would say I'm disappointed that we could be faster in development. The problem is that there is a lot of things to develop, so you cannot do everything. You need to prioritize. On the other hand, I'm sometimes disappointed when I see some latency, or like, of course, it's natural to everyone. Like, imagine company has been developing their procedures, internal processes, using existing tools. And so it's not easy to change that, and to be sure that the new tools will bring expected value. So pace of adoption of new technologies, we can say, may not be as fast as we would like to see it. But on the other hand, we are dealing with a sector which is very conservative. Energy sector and finance, banks are very conservative. They don't like, they need stability. What they really prefer is to have something which works, which is generally accepted. That's what the banks call, that they need bankable solutions. That means something which is trusted by banks. And to change that takes time, but we are patient. We have been over all this in history with data. We were struggling with banks accepting our data for many years until we demonstrated that the weather data, solar radiation data, which we offer, is much more accurate, more can be relied on in various geographies, and it's better to change. So we made this historically with data, and I believe we can make it also today and tomorrow with other digital solutions such as simulation software, analytical software, and so on. So we are used to it already, to this environment, and today the industry already understands what are the pains. They know that they should consider change, but of course it's not easy to, with a big company, to make this change overnight.
Yeah, and maybe just finally back to yourselves. In terms of what we've discussing, you've outlined the technology and the solutions, but I know fairly recent you launched Evaluate 2.0 software solution. So perhaps we can just finish with that. What that brings to the market for.
Yeah, this is over history of quite several years. We decided to develop a completely new software solution on top of our data so that we can overcome long-lasting pain of industry. The pain of industry is that for many years it had to rely on very simplified datasets, low granularity datasets with desktop software tools which had very limited computing power based on empirical simplified models, a lot of assumptions and simple guesses, and lack of collaboration, lack of trust in technical specification of technology which is included in the simulation. So, and this is a complex of quite several big things which had to be changed. So as we already had the high performance database and we were very well known by offering this data, we had already something which is very important for the start. And one of the important motivation for us to move this step was that our data at the granularity and accuracy which we offered, it is not possible to use them in such level of accuracy in existing software tools. You need to downgrade that data. And we were kind of angry because we saw like this is not simply helping anyone. So we developed software which is based on cloud-based services, parallel computing, completely new numerical methods which are able to crunch large volumes of data to deal with large utility scale projects. So we talk about 300, 400 megawatts, like really gigantic projects, able to simulate them at the high level of accuracy with latest scientific methods. That's on the side of simulation. Then in order to run the simulation, you need to have a design software which can help you to create the design exactly as you want. There is a lot of tasks on optimizing the design because there are many ways how you can build a project, but you want to build it exactly in a way which matches your technical constraints, like geographical constraints and business model. So in order to offer such optimization tool, you need to have 3D high performance graphics tools for creating such designs. So that was the second pillar. So data, software simulation design. Another problem is that for sophisticated simulation tool, you need more technical inputs representing the technology, such as inverters, PV modules, trackers. So we had to create the fourth pillar is a technical database of PV components. where you want to rely on the information. There is a large number of parameters which are used as inputs, and you need to make sure that all this is correct. That means you need to have quality control processes which can check that everything which has been used in the database is fitting together. Otherwise, the simulator would result in a fail. So, and then you need analytical tools, reporting tools, so that all this creates an environment which today is offered by Evaluate. It also includes the collaborative method, so that you can collaborate with distant teams, and that's exactly the case how industry is working. People are sitting in various locations. They need to work together on a project, which is only possible today with the cloud solutions. And what also comes as very important, we need to look more and more into cybersecurity. Of course, with the digital tools, I believe this is the case of every single discussion, Phil, you have. It's cybersecurity is becoming a big topic as well. We need to comply with the standards. We need to go together with our customers in improving the way how technology is used, so that we can avoid unpleasant situation. So roughly, this is the situation today with Solargis. We grew from a company of 2 co-founders to 130 plus, and that's I still feel that we are still somewhere in the beginnings, because the digitalization and energy are, I believe, in society and in economics, these are one of the key pillars of the economical growth everywhere. And we are part of it, and that's what makes me happy.
And just to follow up on that, I mean, would you describe your Evaluate to? There's a lot of talk about digital twin technology at the moment. Is that part of what Evaluate does, or is that slightly different? Yeah. Maybe it doesn't matter, but I'm just curious as to that.
Thank you. So I'm happy that you pointed out this term, digital twin. Digital twin is exactly what is introduced in many industries, including solar photovoltaics. You need to be able to describe the project digitally in the most reliable and representative way, so that it serves you not only the purpose of developing, constructing the project, but before that, optimizing a number of solutions and coming to the solution which fits best your technical and financial means. So for that, you need to create very, very encapsulated system where data, technology data, weather data, simulation, visualization, analytical tools work together to create something which is very well representing reality. And what is nice things about all that is that you use this digital twin in the next step, where once the project is constructed, you are using this digital twin for regular monitoring of the system. That means checking whether everything is okay as it should be, and forecasting. So again, forecasting has to always rely on what you were calculating before, and it learns from the operational data to predict the close future. So you can only do that if you have smoothly designed system where the data flow from the recent history to close future is physically aligned, so that whatever you learn from day before, how the project reacted to certain situations such as snowfall, dust storm or something, you can immediately transfer this information to forecast. So and that's where digital twin, that means simulations based on the right configuration, right data flows. That's where it, of course, where is the place of digital twin?
Okay, I mean, I have taken up a lot of your time, and I'm very, very grateful because it's been a brilliant conversation. I've really enjoyed it. You shared some fascinating insights into what is obviously a complicated topic, but it's rapidly developing, and the digital sort of future is fascinating. So, Marcel, I just really appreciate the time you give me. Thank you so much. Thank you.
Phil, thank you very much. Pleasure talking to you. Thank you.